Hello, this is Brother Cromer from the Math Department at BYU, Idaho. And these videos, I will be covering Lesson 13, which is inference for two means paired data. And here will be the outline for Lesson 13. First, I'll be introducing what matched pairs are and what type of data we'll use. Then I'll follow up with that with hypothesis testing, then with confidence intervals, and then finally we'll wrap it up with checking requirements. These last three items, you see that on a regular basis. In fact, you'll see that all throughout Lesson 2 we'll be covering a way of doing a hypothesis test, doing confidence intervals, and then checking requirements. So first let's talk about matched pairs, or paired or dependent samples. This is the type of data we need, paired or dependent samples with doing with matched pairs. So basically, individuals in one sample are used to determine the units or individuals to be in the second sample. So if you look on the bottom right, you see a set of data where we have 13 sons and 13 fathers. So we can ask the question, are sons taller than dads? So if we take a random sample of 13 sons, hopefully it makes sense that automatically the dads will be selected. So the second sample is dependent on how the first sample is selected, meaning in this case, how the father's sample is dependent on the son's data, or the son sample. So either two units can be paired together or two observations can be paired with one unit. Now in this case, there are two units, one unit being the father and one being the son, are paired together. Now there are other examples of this in both cases, and I'll go to the next slide to show you that. So for instance, with a similar situation that we saw with the fathers and sons data, do married people have similar IQs? Now here we have one unit being husband and one unit being wife. Those are paired together. We want to see if married people have similar IQs. Those are paired together. You could also argue that one unit is married couple, and so within the unit there are two observations. Now the other example where we have two observations paired with one unit is an example of that would be pre-test versus post-test data. We have a pre-test, as students, we take a random sample of 6, we take a pre-test for a class, for instance, and then we follow up with the post-test. And then in this case, there's two measurements for each, or two observations for each unit, one unit being student. Now here's another example of it with which two methods in Scouts is faster for starting fires without using a match. So the two most common cases are two common methods would be flint and steel and battering steel wool. Now we can take 6 Scouts, for instance, and we can time them with the two different methods. These two times represent two observations for one unit, the one unit being Scouts. So these two are very similar to each other, pre-test versus post-test, and methods in starting fires. Now let's talk about hypothesis testing. Okay, so now with hypothesis testing for matched pairs, I want you to see that it's similar to a one-sample t-test. Matched pair t-test is similar to one sample t because it's basically one sample of differences. As you saw, what we do is we take the difference between the fathers and sons and we get a column of differences. And what we do, now if you remember back in lesson 12 with a one sample t-test, this is the test statistic for that. Notice down here the test statistic is fairly similar to that. Okay, so what we do is that we get this column of differences and we get d bar, which represents the mean of our differences. And we also get the S sub d, which is the standard deviation of our differences, and we divide it by the square root of our sample size. The sample size is the number of pairs, which is 13. Now notice here we have 0 as to the right of that, and I'll talk about that later in terms of why it's 0. But basically, when we do a paired sample t-test, it's like doing a one sample t-test, but with a column of differences. Okay, so let's go through the 6 steps of doing hypothesis testing for matched pairs. Step 1 is state the null and alternative hypotheses. Now notice how I write the null hypotheses here. It's mu, which is the mean, subscript d, so the mean of the differences is equal to 0. Basically, between the two columns of information, the columns of data, there is on average no difference statistically. Okay, the alternative is that it's either less than 0, greater than 0, or not equal to 0, meaning that the mean of the differences is either less than, greater than, or not equal to 0. Okay, and it depends on the test whether it's a one-sided or two-sided test. Steps 2 through 4 will be computing. We'll be using software for that, computing a test statistics. Step 2, degrees of freedom. Step 3, and p-value. Step 4. Steps 5 and 6, they should be awfully familiar to you because it's no different than what we've done before. So the decision rule for step 5 is reject the null if the p-value is less than the level of significance, and then if it's not, then we don't reject. And then we state our conclusions, which is no different than what we've done before. If we reject the null from step 5, excuse me, we have sufficient evidence to say that, and then we state the alternative in plain English. If we don't reject the null in step 5, then we have insufficient evidence to say that, and then we state the alternative hypothesis in plain English. Let's go through a couple of examples. Okay, so using the father-sons data, do sons have different heights than dads? So we take a random sample of 13 sons and dads, and we set a level of significance of 0.05. So step 1, we state the null as mu subscript d. The mean of the differences is equal to 0. The alternative is as mu subscript d, or the mean of the differences, is not equal to 0. Well, why not equal to? Because we only want to see if they're different. We want to see if sons are less than, or greater than, or taller than, or smaller than. Then we would have a different symbol here for the alternative hypothesis. Steps 2, 3, and 4, we use software for that. And so what I have here on the next slide is an example of what we see in SPSS, which is similar to what you see in Excel. But in SPSS, this is where we get our test statistic, which is step 2, degrees of freedom, which is step 3, and then our p-value, which is step 4. Now in SPSS, since we're doing a two-sided test, then we leave that alone. Our p-value is 0.702. Now when we go back to the last two steps, our p-value is much greater than our level of significance, which is 0.05, so therefore we don't reject the null hypothesis. And then since we don't reject the null, we therefore say we have insufficient evidence to say that the heights of fathers and sons are different. Okay, so now let's go through one more example here. So this is from the online textbook. 27 women participated in the 9-week weight loss study. During the study period, the participants were provided a reduced calorie diet. Their weights were recorded at the beginning of the study and 9 weeks later. The difference of the weights is defined as the post-study weights minus the pre-study weights. The researcher expects that the mean of the differences in the weights would be negative. In other words, the women would tend to lose weight. Test the women's weight would decrease significantly with a level of significance equal to 0.05. Now step 1 is state the null and alternative hypotheses. So the mean of the differences equal to 0 is the null. And the alternative is that the mean of the differences is less than 0. We're looking for a decrease, so we would do a left-sided test. Steps 2, 3, and 4 are right here, the test statistic, the degrees of freedom, and the p-value. And so what I have here, I'm going to go to my output in SPSS. This is where I got an SPSS. Like I said, in Excel will be different. Will be similar looking, but it'll be slightly different layout here. But this would be the test statistic here, degrees of freedom, and p-value. Now in SPSS, parenthetically, since usually SPSS does a two-sided test, we have to take that number and divide it in half. But notice here that it's 000, which really means it's very close to 0. Okay, so since it is close to 0, we do not reject, since it's close to 0, and it's much less than our level of significance, therefore we reject the null hypothesis. And then we reject the null hypothesis, and therefore, in step number 6, since we rejected the null, we have sufficient evidence to say that the weight significantly decreases with the weight program. Okay, so the last step, I stated this in English, referring to the alternative hypothesis. So that concludes part 1 of the video. So when we get into part 2, I'll be discussing confidence intervals and checking requirements.